Hello, and welcome to our video for 10.5 to 10.6. I know the sections and chapters are weird here, but this is still part of the Chapter 9 chapter, even though we're technically in Chapter 10. We're still talking about significance tests, though, that's why. But specifically, we want to look at paired data. And what this means is that we're looking at two sets of data, but then we're going to look at the difference between them and then calculate an average that way. So paired data itself counts as data from pairs of very similar people, like if we had twins or something like that, because they're very similar to each other, or if you had two sets of data from the same people. So like if you had one group of people and you were looking at the data of something you measured before and then measured from the same people again after. So in order to analyze our paired data, what we want to do is to take our two sets of data and actually find the differences between each of the numbers. So in this case, we are looking at data from twins. They were separated and adopted at birth. In each case, one twin was adopted by a high-income family and the other twin by a low-income family. We want to look at their IQ test as adults. Here's their scores. So in order to find differences, all we're doing is just subtracting. So like for the first set of twins, they have to be matched together. So that's why it's called pair 1. Because we want to make sure, the twins that are actually twins with each other, their data gets subtracted. So 128 minus 120 would give us 8. We can do this for the rest of our data. Of course, we are lazy people, so we love to do things in our calculators. So what we're going to do is type in everything from twin A, or our first set of data, into L1, and then our second set of data into L2. Alright, so I input all my data into L1 and L2, and then we're going to scroll over to L3 and have our calculator subtract everything for us. So we're going to subtract twin A minus twin B. So when I highlight L3, I can type in L1 minus L2, and it'll do all the subtraction for me. So these are the numbers we actually want to look at. These are the differences. So when I'm testing a claim about a mean difference, really, I'm not using any of this data here. I'm going to use my set of data that are just the differences. So we really only focus on L3. So now I have all my differences. In order to analyze this, we want to calculate the mean and the standard deviation of the differences. So obviously we can do this by hand, but we have our calculator. We already have all our data in it. So we're looking at the mean and the standard deviation of our list in L3. In order to do this quickly, if we go back to our home screen, we can do stat, go over to calc, and then the first one of our stats. The list that we're looking at, though, is L3, and then we can calculate. The mean is 5.8333. The standard deviation is where SX is, so 3.9273 something, something, something. Okay, so as usual, we're going to do four decimal places for everything. Alright, so then once we have the mean and the standard deviation, that's the numbers we're going to use in order to calculate our test statistic, and then our p-value, and so on. So I've written out the calculator directions here, just in case. So let's actually do this with an actual full significance test. So in this example, we've got SpongeBob and Sandy at their local bargain mart. So of course, in our last video that we make, of course we have to have a SpongeBob example. So they're wondering which lane is faster at this bargain mart, the express lane or the regular lane. Sandy, being the scientific one, decided to collect data by randomly selecting 10 different times to go to bargain mart, buying the same item each time. Either SpongeBob or Sandy would use the express lane and the other would use the regular lane. This was decided by flipping a coin. They entered the lanes at the same time, paid with the same method, and recorded the time in seconds it took them to complete the transaction. Here's their data. Okay, so we are looking at the data for how long it takes them in the regular lane and how long it takes them in the express lane. So let's see if there's convincing evidence that the express lane is faster on average if we're using alpha, our significance level of 0.10. So first, let's write down our hypotheses. They're going to be formatted slightly differently, but generally still the same: equal signs, less than, greater than, whatever. That process is still the same. So here we go. For our HO and HA, we are dealing with averages here because it says which lane is faster on average. So we're using mu, but because we're dealing with paired data here, it's going to be written slightly differently. So the symbols we're going to use is mu with a little subscript d, d standing for difference. So instead of just a regular mu, we're just letting people know we looked at the differences from two sets of data in order to calculate our average. So our null hypothesis, whenever we're dealing with differences, is always going to be 0 as our number. We're basically saying there's no difference between the two sets of data that we have, because if I were to subtract, and if they were the exactly same number, then we would subtract and get 0. For our alternative hypothesis, we're trying to find convincing evidence that the express lane is faster. So this part's a little bit tricky because we know what the number we're using is 0. The sign that we're using, whether it's less than, greater than, or not equal to, that is a little bit trickier to decide, because when we subtracted, we're usually going to do like the top one minus the bottom one. So that means we're doing regular minus express lane for this problem. So if we want to prove that the express lane is faster, then that means all of our express lane numbers, if it's actually faster, should be smaller numbers, because if you spend less seconds in the express lane, then it's faster. So that means less seconds and smaller numbers in my second set of data, which means the first set of data is bigger numbers. So when I do a bigger number minus a smaller number, I should get something positive. So positive is when it's greater than 0. So that's how I decided it would be greater than 0. If I was trying to find convincing evidence that the express lane is slower, then that means my second number would be bigger, and when I subtract a smaller number minus a bigger number, then I get negative, and that's how I would be less than. So if they don't say anything about faster or slower, if they're just asking if it's going to be different, that's when we would use the not equal sign. But here's our hypotheses. That's done. We're checking our conditions. It's the same conditions as before. We want random samples, and we want it to be approximately normal. So in this question, we don't have random samples, but they were randomly selecting 10 different times to go, so it's like that counts as our random sample. And then to check if something is normal, then we need our sample size to be greater than 30. But in this case, if we were to find all our differences from our two sets of data, we're only going to have 10 data points, which is not bigger than 30. So in this case, if we don't have sample sizes bigger than 30, then we're going to make a graph out of our data points and make sure we don't have extreme skew or any outliers. So let's do that in our calculator first. So we're going to type in our regular lane into L1, express lane into L2, find the differences in L3, and then graph our L3. So here's my L1, L2, and then L3 is going to be L1 minus L2. There's all my differences. So if we want to make a graph of this, we're going to go back to our home screen first, so second mode, and then we want the stat plot. So second, that button, make sure it's turned on. So we want the box plot with the dots, make sure that's chosen. Our X list though, not L1, we're dealing with all our differences, so that's an L3. And then go back to our home screen, zoom 9 will make our graph really nice for us. There we go. So none of my whiskers are like really extremely longer than the other, so this is pretty good. No extreme skew, there's no dots at the end, so we don't have any outliers either. So we're just going to sketch that out, and then that'll show normality. Alright, now that I've checked my conditions, we can move on to our test statistic. The test statistic formula is pretty much the same as before. So plugging into my formula, I'm going to need to find my sample mean. The mu d is the number that we used in our hypothesis, which is the 0. And then we're going to have to find our standard deviation. N for us would be 10, because we have 10 data points. So in our calculators, let's go calculate our mean and standard deviation. So stat, go over to calc, number 1. We want it in L3. Calculate. So our mean is going to be 28.4, standard deviation of 66.5602 if we do 4 decimal places. So here we go. I end up with a test statistic of 1.3493. So now we're using that to find our p-value, same steps as before. So we're using TCDF to get there. We're doing second bars, number 6. Our lower is going to be the negative 100,000 giant number, and our upper is our test statistic, so 1.3493. 0.493. Degrees of freedom is n minus 1, so our n here was 10, so it'll be 9. Paste. Enter one more time. And for this problem, if we were to draw it out on a normal curve, we would be shading to the right because our HA was pointed to the right. So since it's to the right, we're going to have to do 1 minus this number in order to find our p-value. So 1 minus this number. So this would be our p-value, 0.1051. And so finally, we're comparing our p-value to our alpha level. So 0.1051 is a number that's bigger than 0.10, so because of that last 1 at the end. So if it's bigger, we're going to fail to reject. And if we fail to reject, then that means there is not convincing evidence that the express lane is going to be faster. Alright, that was the last video. Thanks for watching. Don't forget to like and subscribe. Bye.